Hi everyone. I am Ganesh, a senior data scientist in Mastercard, and welcome to my talk on knowledge distillation in white box large language models. So, as we all know, LLMs have achieved remarkable success in a lot of tasks, especially smaller LLMs, which were the state of the art back in 2018, 29, which had very less parameters. Now, with an explosion in number of parameters, it is capable of doing so much more. And I think there is nothing which can explain better than the GIF right there. But obviously, with great power comes great responsibility. And that means this significant performance does not come with its own costs. So, and the cost here is essentially significant computation and memory requirements. Now, especially when you're deploying a model to production, especially in real-time scenarios, and by real-time scenario, I can just give an example on Mastercard itself. So here in Mastercard, we have around 500 million plus transactions every day, and that obviously means you need a model to score within a matter of milliseconds. And when you have something as huge as an LLM, that is just not going to happen. So you need to keep in mind various other parameters. It's not just a fact that, okay, it's giving me great outputs. You need to sort of take into account the inference latency, which is the time a model takes to sort of take an input and also generate a prediction. And this system should also be able to handle multiple users pinging it at the same time. And the second, obviously, and I think it has been talked about multiple times, is the sheer robustness and stability factor. Like LLMs, as we all know, can produce hallucinated responses, and even like small changes can drastically affect. And the last and probably one of the most important factors is scalability and sustainability. LLMs, as we all know, consume a large amount of memory. And as we all know, like we would all like to have a lot of cloud GPUs and TPUs, but we know they're expensive and every single sort of hit costs you a lot of money. And that means like you need to sort of conserve that. And the last part is obviously ensuring when you're democratizing AI, it is vital to ensure you have like sustainability in mind. And that means smaller models which consume like much less resources. Now, keeping that in mind, what are the different strategies we can go about compressing models? So the first bit is quantization. So quantization here essentially means reducing the number of bits of parameter. And bits are, in slightly more technical terms, flops is a way of like computing the memory requirements of an LLM, like how precise the weights are. And by just reducing or sort of compromising on the precision of the weights, you can keep the performance. I mean, you can compress an LLM, and there are obviously two, three ways of going about it. First, you have quantization aware training, where you first reduce the weights, I mean, reduce the precision of the weights, and then train it. And then you have a scenario where you already have a big model, and then you quantize it. Now, as you can guess, the problem here is the fact that, especially in like post quantization training or even quantization aware training, you still need to train the model on all these parameters, and that is very expensive. And second, again, like the performance benefits and like the performance degradation is also sort of unknown. Now, another way you can go about it is pruning. And as the name indicates, it just means cutting it off. Now, you can go about it in three ways. You can go about it in a more structured way, which involves sort of removing entire layer or just an attention head, just like that. Or the second part, which involves unstructured pruning. And what this means is you remove individual parameters instead of like, entire layers. And this sort of gives rise to an irregular sparse structure. And the last bit is essentially just a sort of best of both world scenario, which is called semi-structured pruning. And again, the problem with pruning is the fact that uh, a lot of the times, like the effect of pruning, because of the fact that we understand very little about these huge black box models, is very less known. And sometimes, like when you prune a certain large LLM for one task, let's say summarization, you might be pruning the important parts for another task, which is probably, I don't know, question answer retrieval. So that is also one major consideration. Now, the third, low rank factorization, again, something which has been explored a lot, which involves decomposing these large matrices into smaller ones. And again, like one major problem with low rank factorization is the fact that, again, like uh, some, like obviously all of the weights might be like large matrices, but like it is not fully clear as to like which weight you want to like sort of factorize and which weight you want to keep. So that part is again needs a lot more exploration, to be honest. And again, we're coming to the last one, which is knowledge distillation, which is transferring the knowledge from a teacher model to a smaller student model. So why focus on distillation? Why not the other ones? And this is because of three factors. So first being, it's not just a simple compression. You're not just randomly, let's say, removing neurons or reducing the number of bits. You are transferring the knowledge in itself. So the student here learns to mimic the output behavior of the teacher. And the student is inherently task aware. And what I mean by that is you are training the student on the task you want it to perform on. Unlike, let's say, most of the pruning techniques or most of the, let's say, quantization techniques. And second is the fact that, and the second and third are probably the most important benefits, considering there are task aware training techniques coming up for the other ones, is the fact that there is a flexibility in student model design. Like in the case of quantization and pruning, I'm still limited to the LLM. Here, we can pretty much like use whatever model. There are ways of like doing cross model distillation and everything. So there is a lot of flexibility. And that means like depending on your resource constraints, depending on the deployment constraints, you can create tailor made like lightweight models. And now the last part. So what pruning, low rank factorization, and uh, quantization is inherently limited to is that one big model. Now you can build 10 big models and sort of quantize all of them separately. But then that is again not really a scalable or a viable technique, right? So what this lets you do is you can actually combine information from multiple big teacher models, and then you can like, and it's essentially uh, like philosophically speaking, it's just a way of blending knowledge from multiple experts, and this can give you an ensembling benefit, which the other structural methods just don't offer. And now, why specifically white box distillation and why not like black box distillation? So before I go into the depth, just a small intro as to what white box distillation and black box distillation is. Uh, Black box distillation is generally limited to the proprietary models, which involves like ChatGPT, Claude, all the famous one you would have seen. Here, you only have access to the outputs, which is like the sentences you get or even the tokens, but you do not have access to, let's say, the probabilities or what happens inside the model, the weights, the activations. White box distillation is in a scenario where, for an open source LLM, something like a Llama or a Quen or a DeepSeek, or even something your own organization, let's say, decides to develop a model on their own, there you still have access to the weights, right? And this means like there is so much more you can do. And there is so much like the richness of information you can get from the teacher is much more nuanced because you have full access to the internal layers, the representations, the gradients. And what that means is you can leverage these sort of intermediate representations to make and like model the student better. Now, before I explore certain techniques on model distillation for like LLMs, what exactly is model distillation? For that, let's take a step back into the vision world. So, the whole concept of model distillation was introduced by Geoffrey Hinton, who we most of us probably might know is a pioneer in the field of machine learning and especially computer vision. So, here he took the case. So, let's take the case of MNIST, where you have multiple numbers and you want to sort of predict like which digit does a certain number corresponds to. And I know let's probably even take a step back from machine learning itself and talk about like how teaching happens. So when you're teaching something, you don't just say whether this is a nine, like you also say as to why, let's say, a nine does not look like an eight or a three. And whether it looks like a nine or not is essentially what your cross entropy laws, which is the standard like laws, tells you. But how exactly a nine is, let's say, different from a two and like slightly similar to an eight, because there is that small zero out there, is what you want the student model to learn, because there is inherently a difference between a zero point 0.9 probability versus a zero point 0.6 probability, and that is what the teacher model has learned, and that is actually what enables the teacher model to perform as well. And now when you train a smaller model just using the fact that whether a 9 is a 9 or not, obviously, as we would have seen in multiple studies across domains, it doesn't perform as well. But when it gets that supervision from the teacher as to how correct or like how wrong the other outputs are, then it gets a better idea about like how to sort of model those hidden representations better. And again, this predictive probability is also colloquially sort of known as soft labels. Now, these distillation techniques can be sort of broadly categorized into two groups. So the first involves divergence-based KD. So this involves minimizing the divergence between teacher and student probability-based distributions. So what that means is you typically have something like a KL divergence, as we discussed, or some other divergence-based function, which we'll discuss later on in the slides. And what this lets the student do is it enables the student, as I said, to match the decision boundaries. And by matching the output behavior, the idea is that the student learns to sort of think like the teacher. And the second is obviously you can align the hidden state of the student with the teacher. And I know the equations look a bit scary, but all it essentially says is you map the teacher and you map the student to a sort of shared space and then sort of minimize the discrepancy. And what this lets the student do is it internalizes the layer wise behavior, and you're essentially learning, the layer wise behavior and activation of the teacher in itself. Now let's delve deeper into divergence based KD methods. So I'll first talk about this method called mini LLM, which is a recently developed framework that leverages reverse KD. Now, in the previous example, I know we talked about forward KD, but there is an inherent problem in using forward KL divergence methods in LLM tasks. And that means when you there is a like first of all, KL divergence itself is inherently asymmetric. And what I mean by that is KL of P and Q is not equal to KL of Q and P, right? And this diagram I think explains in a much more beautiful manner, which is that when you do a KL of P and Q, the student is forced to match all of the teacher nodes, as you can see in the left. And that means like even in the void regions of a teacher, the student is still forced to give sort of a non-zero probability. And what that means in the context of, let's say, language means uh, the student will start hallucinating and start creating like low quality outputs. So let's say if the passage is about Paris, it might just start talking about, I don't know, generative AI in general. So yeah, like whatever low quality output is, it'll start prioritizing it. It is suitable for structured tasks like let's say classification, which is what the initial algorithm was developed for, because there you only have like two, three nodes. Like a number can take an MNIST data set is just like 10 digits, but not for sort of an open-ended generation. So what this paper does is it introduces something called as a reverse scale divergence. And what that means is just by flipping it, you are making the student from a mode covering behavior to a mode seeking behavior. And what that means is now the student wants to prioritize the bigger modes. And that means like it prioritizes tokens with higher teacher probabilities and it assigns lower probabilities to all the void regions. And that means the chance of hallucination is much lesser. But then again, just using reverse scale divergence doesn't solve all your problems, because this leads to something called as a reward hacking behavior, where now the student starts outputting very nonsensical and like very a lot of repeated phases, very short phases, because again it sort of prioritizes like small length outputs. So you need like different techniques like single step decomposition and also like length normalization, teacher mix sampling to sort of mitigate this reward hacking and length bias behavior. So a much more recent paper called GKD sort of develops a more generic framework which unifies all these various loss functions. So what GKD is essentially inspired by is the fact that even in the first case, and even in probably most of the classical knowledge distillation cases, there is a data set. So let's say you're talking in terms of a legal scenario. Like I'm not a legal expert. I'm just giving like very simple examples. So let's say you have a model which is trained on like constitutions across the world, and you want something specific to, let's say, uh, some contract law for Hollywood, just giving examples here. And now what that means here is now you would create a data set sort of specific to that and then train the student to sort of match the distribution of the gigantic LLM, etc. But if you look at like recent work which involves fine tuning and like enabling LLMs to sort of reason better, students actually perform much better when they actually learn on their own samples. So not just the data set you feed them, which was like the initial approach. If the student is able to learn from its own mistakes, and it's called imitation learning. And what this means is if you can enable the student to receive token specific feedback, this can sort of simulate a reinforcement loop, because the student is not only learning from your golden data set, it is also learning from itself. And this sort of reduces the train distribution and the inference distribution mismatch you clearly see in a lot of cases. And because the sampling process itself you're not sort of iterating over that. The process is computationally efficient and scalable. And what they've done is they've sort of unified these two techniques. So as you can see here, like you have a divergence. You can use, first of all, like you can use a forward scale, you can use a reverse scale, or the more general divergence called the Jensen-Shannon divergence. And I know before, I don't want to get more theoretical here, but the idea is Jensen-Shannon divergence just sort of balances out the forward scale and reverse scale, and it's using a set of hyperparameters. You can sort of control how important each loss function is. And again, as you can see in the above equations, you can sort of control how important each term is. So how much importance should the distal data set take? How much importance should the student give to its own sort of learning loop? And one more uh, interesting benefit is the fact that it has a high synergy with RL fine-tuning techniques. So generally, again, like in the case of, let's say, you have a gigantic LLM trained on one task, but your smaller model might be trained on a similar task, but not exactly the same task. So this sort of, when a student learns from a teacher, it might learn too much from a teacher. And that means, and because the downstream tasks are not inherently aligned, this might lead to a performance drop. So combining it with something like an RL fine tuning technique like RLHF or even PPO, GPO, this sort of enhances the capabilities and maximizes rewards. Now, let's delve deeper into hint-based knowledge distillation methods. Now, in the previous slides, we sort of discussed about how to take the probabilities and then sort of build an approach where the student matches the decision boundary. But when you have access to weights and activations, why not use it? But there is a pitfall with like using it in a naive manner, which is just like, let's say, using a simple L2 loss or an representation similarity loss over two. One is just the sheer fact that the student will struggle to mimic the teacher due to misaligned internal representations because you have a much bigger teacher and there is a smaller student. And second, there is also a possibility of redundant knowledge transfer. And like a lot of teacher, because the teacher has a lot more weights and a lot more parameters, a lot of this information present in the teacher is not really relevant to the student or the task. And the student might focus too much on those tasks while training, and this might not lead to optimum outcomes. So it's important to sort of consider a selection mechanism to reduce this gap. And how they go about it is by training task aware filters. So in phase one, you sort of freeze both the teacher and student models. Then you train task aware filters, which are these small neural networks with task specific heads on top of frozen layers. And these filters only extract the predictive knowledge relevant to the task. And now, once you've fixed this, then you keep the teacher and the teacher's filters frozen. And then you train the student and the task aware filters in a joint manner. And you also introduce a task specific head uh, in the end, just to ensure like you penalize the discrepancies between the student and the filtered teacher signals. Now let's look at some of the results. So on your left, you can see how well Mini LLM, which was the paper which introduced uh, reverse scale, performs. And here you can see how, yeah, sorry. So here, this corresponds to multiple experiments done on GPT-2, Llama, and OPT, and again on multiple parameter sizes. And you can see how even 7 billion parameter model is very close to the teacher performance, while other models sort of struggle to reach the same performance. Uh, Again, and if you look at the performance of the generalized KD divergence on GSM 8K data, and GSM 8K is a very popular reasoning data sets. In most of the cases, it performs much better than a student trained on simple few shot COT prompting. And again, the idea is that the student is learning much, and even the other sort of knowledge distillation algorithms are performing much better than a simple uh, student model trained using some chain of thought prompting. And obviously, the on policy GKD performs much better. And now, okay, now that we have examined multiple works related to white box LLMs, what are some of the best practices recommended? First and foremost is obviously garbage in, garbage out. I mean, you need a good data set and it has to be diverse. It has to be representative of the kind of situations and scenarios the model will face outside. So there should be a proper representative data set. And it's also important to keep in aware fairness conditions and also robustness, because there has actually not been much studies done on like how exactly the bias present in a teacher model propagates to a student model. So that needs to be studied as well. And again, the robustness. So how strong is it to some random attack or some adversarial attack by small, like slightly varying their inputs. Uh, and it's also important to understand that uh, the other hint-based mechanism method we discussed, and most of the hint-based mechanisms are only primarily developed for bird-based architectures. So a more in-depth understanding of various LLM architectures can facilitate more effective techniques. And so it's important to consider all these techniques, let's say forward KL or reverse KL or even like a simple L2, and understand that it depends from task to task. And it's vital to sort of leverage a strategic combination of all these methods, and that will get you the best performance. So it's all task dependent. And again, like it's a great way for like organizations to create one generalized universal LLM with, and they can keep improving on it while ensuring for each department use cases or each specific other productionalized use cases, you have like smaller LLMs which sort of learn from the bigger LLM and it's tailored towards more specific business specific needs. So thank you all for coming and attending my talk.